thank you for coming to this last talk of the morning. The previous talk you heard is a good, gives a good go forward to this talk, because she talked about the rest of the world, the rest of the universe. I'm going to talk about this Earth, that we had to work on problems which are of daily requirement and satisfying the needs of people in a certain limited way, like low cost, low error kind of thing. So this is the opposite of what you heard. We could someday put together the two of them in the same slide. So the talk is about smart systems. How many of you know about smart systems? Have heard of smart systems? How many of you are carrying one? Put up your hand. It's a good bit of exercise also. So, anyway, smart systems, you'll hear the technical meaning of this when I go forward. I'm from IIT Bombay, actually, but I'm currently in Sai University, helping them to establish a department of data and science, data and all the other sciences. But fortunately, there are only so many now, not in millions, but in tens of numbers, in numbers. So I'm going to talk about the way in which we can solve problems, or address the questions that people have in the context of energy management. But this is a more general purpose use, as you'll see. So what is smart? Smart involves producing enough answers and in sufficient accuracy that it will be useful. Okay, the world is changing continuously, as you just heard, and how do you, in spite of the world changing continuously, how do you sense meaningfully? How do you sense? How do you analyze? And how do you respond? That's what we do, right? We hear people talking. We try to see how two such conversations can be put together to get something of larger magnitude, larger accuracy and so on. Yeah. So the point is, if you hear everything around you, try to put that together, that will be meaningless. So they'll be in different domains, different kind of approaches to handling the data and so on. So how do you decide what is meaningful? That's one of the questions. We normally decide based on our background, what is part of the psyche, the brain, and so that is how we learned how to do meaningfully. But there's more than that. There's something you can specify and be strict about it. And analysis, all kinds of analysis tools are there. The result of the analysis goes into this third box, where some more processing is done to determine who is going to be looking for the data. You respond to that, and also you hypothesize that you will have more people, more locations at which this data will be useful. So you want to remember that and go on and publish the data to that group. So that's the basic idea behind sense meaningfully, analyze and respond and remember to do it. Now, why does remember? Remember is there because we all do this, what's called reinforcement learning. You all know about this because the Nobel Prize was won by people who worked on this topic. So how do you know who requires it, and how do you know how to send it to them? So part of the mechanics of executing this sequence, and that timeliness is also important. See, if you read some paper today, there's an article in it. If you just tell somebody a month later, they won't have any interest in it. You want to give the answer, pass on the answer in a fixed amount of time, and that too. You may have different deadlines for different kinds of importance levels. You want to adjust that according to what's available in terms of resources. Are you with me? So we have sense meaningfully, analyze and respond and remember as the third element of the cycle. This keeps on going. As we go along, as we walk around, we gather more data, throw away some of that, keep the remaining. That affects your subsequent dealings with the machine, and then you go decide what to do with it and respond accordingly. Okay? So that is in a timely way. Now with this in hand, we can do other things. Then we add them together. For example, if I'm doing a smart principle applied to energy management, I see that there are three important questions to ask. How do you use energy carefully, and in particular, you don't want to have unnecessary consumption of that increases the cost of what you are consuming. So we want to avoid unnecessary consumption. Second is it might be available all the time, but different times have different costs. This is true of energy. In the night, it is cheaper. In the mid-afternoon, it's very expensive. And evening, it depends on the consumption that's going on. So we have a lot of variation coming from the different inputs and the output that's produced, how they're used. And so to make use of that, we'll use a technique called opportunism, where we flatten the peaks, because peaks are not always good. Peaks in energy production especially can be very bad. Most of the production of energy is of a kind where beyond a certain point the cost increases exponentially. That's why we get the whole problem with carbon-based power, because we have the carbon footprint to worry about. So what we'll do is we'll flatten the peaks. Normally, if you see a picture of this, if you see a picture of the consumption profile, it will be exponential in nature, coming down quickly, increasing, coming down quickly, and so on. So what will happen is that when we have energy which is being used by a large population, and it is not of a constant type, then we have to worry about the peaks that will appear and use techniques to minimize the effect of the peaks. And third one is to use the right energy sources. At night, you don't want to use the sun; it's not there. So you want to produce enough energy, enough so that you can store the energy required for the night. Right? So that is called that I'm denoting by exploit renewables. Now, and so you do that by storing excess energy during the off periods. Nights, if nobody's using it, there'll be some amount of energy produced from the other types, which are the type where you can store it. If you don't need it, then that stored energy is not going to be used. But the off-peak period is important to use that. You don't want to start storing things when things are expensive, right? So here we have a list of techniques to be used for satisfying certain requirements. Less energy, opportune time usage, and right energy sources. Oh, okay. Let's have this. So I'm going to take you through three examples. So if you have a need for any technique which is based on this, let me know. All of these have been implemented, tested, and they're good and bad ideas have been identified, so we can help you with that. So, for example, suppose I use this technique of smartness from using techniques in such a way that they can learn from one cycle to the next. They can learn from neighbors, and you can also monitor the system yourself to figure out how things are moving. So here we have a smart classroom where we have applied many of these techniques. You'll see that in a second. There are about 10 examples we can give you, which have been implemented and all that. But I'll focus on 3 or 3.5, and depending on time. So the first, this example, what we are aiming for is to make sure that there's energy consumption only if there's occupation in a space. Right? For example, if if you go to an auditorium in a university, you'll always find that this is on. Because it's the easiest thing to do. And it's also true of classrooms and some faculty offices. So you don't have that being satisfied. What will happen is that you will have energy being used, but nobody is sitting in those spaces, or no need for that consumption going on at the time. So how should we worry about this? We should first thing we do is to create a state machine that which tells us what states you go through and what triggers the state transition. So you have here, we can't probably read it, I'll take you through this. Okay, we're moving already. Okay, so first is you have cameras in the room, and they tell you what you're looking at. So this first thing says head found, head not found, as the case may be. Then others are lights, fans, those are marked in the circles. And the edges represent the transitions. For example, when you're in a head not found situation, we can see that you're going from a state which is, says HD, HND going to HD to the HD state, right? So that means that when you're in an empty state, nobody is there, then the head appears, detected by the sensors, then you're going to get to the state where it says occupied. Okay, with me? So, then from there you have stuffiness, hotness, chillness, all of those possibilities. Depending on what really happens, it moves to one of the other states. Bottom line is, if you look at this movie clip.
Yeah, there's going to be a movie.
Yeah, stay for it.
Yeah.
So now you got the idea that things move as the state changes, and it's up to you to go to correct state so that the semantics of the application you're in for, that is satisfied, the cost is low. Okay, low by design. And here we have a situation where we all know about the way rooms are scheduled in our offices. The classrooms are always on. The AC is on, lights are on, and people come in and go. Nobody takes responsibility for the adjustment of the AC's switches or anything like that. Because of that, there's a lot of energy wastage. I'll show you some examples. Okay. So the examples illustrate to you that very simply you can understand what the state is, and how you go from one to the other depends on the state that prevails with regard to the space in the room. For example, let's look at this this auditorium. So these boxes represent a particular slot and which class is being held there. Okay, for example, you see CS 743 to 31. 743 is going to be held there in room 201, and if we have more than 50 people, they can't be managed. They have to reorganize it. But that's the assumption people use because the office has given them the requirement. Okay. What we do here is to show that if you have a class schedule which is based on all these inputs from the various sources, you will come to a situation where there might be some mistake in the assignment of the rooms, or you're going to have rooms attached to people or courses which are not appropriate for the situation. Okay. So now during this process, you'll also see that sometimes you have a space allocated for 1 hour for a class. Next hour is free. The third hour is used again. What do you do in this case? You automatically say, let's close the AC for 1 hour. But we know better, right? Because we know in the nights when we go to sleep, we keep the fans at a certain value for the set point, which will allow you to move forward without paying the price for the 1 hour of spent fuel on AC, right? So now can we do this more methodically? Methodically, that's what we show here. The scheduling is based on pre-cooling, where we use the fact that it's been around, and the room is not being used now, but that doesn't mean it's not going to get used. So the requirement I had there, which said that you should use, if I can remind you. So energy consumed only if occupied will be satisfied only in cases where there's no other hope to use that the cool situation, which is produced using energy.
Okay. I'm going to just go through the rest of the slides for him. This is all his work, but just because he has a little bit of difficulty in projecting his voice, can I just go through these slides very quickly? So this is based on class size is one parameter, and pre-cooling that is talked about is the other parameter. So you see that just by using those soft information, fusing them with the smart solution where there is no occupancy, nothing is turned on, you could save a lot of energy. So in the next slide, this slide shows the baseline is in IIT in computer science department. The morning 9 o'clock, somebody will come, the security will come, turn on all the lights and fans and the HVAC systems in all the classrooms. And they are turned off only in the evening after the classes were over. That was the practice before. And then if you do, turn them off during the lunch break, then you saved some energy. These were all instrumented, verified, measured, verified in the computer science department. And the appliances, if you just actuate them based on occupancy, the smart, if you use that principle, you already saved 31% energy. You save it, the pre-cooling, if you use the pre-cooling factor, you saved 41. But you also used the smart schedule where you map the class size to the room size and use this pre-cooling effect. You could save up to 58% energy, and this was demonstrated in IIT Bombay. And also it only takes about 6 academic months to recuperate the cost of doing all these sensors and other artifacts that you have to come up with. So this is very interesting finding. Now moving on to example 2, that was a classroom space that was instrumented. Here this is an auditorium like here, FC Kohli Auditorium, where again, it was shown that just by reorganizing the seating arrangement, if it is not occupied completely, you ask people to move forward to the different zones and only use the lights and fans and the ACs in that zone, you could save a lot of energy. And it was shown that 30% energy. So we had to tell people, can you please move forward? Because people usually like to sit in the back rows, here, there, everywhere, right?
Ma'am, 1 minute.
Yeah.
1 minute.
So this is the second example that we wanted to show, and this is all the research that went on to even map the heat distribution in a big auditorium, and a mobile app was developed to do all these mapping, and without compromising on the user comfort, you could have a seating arrangement that was conducive to user preference also. So this is an example that we wanted to show. And finally, the smart door, which, if you have a lab-like space, you could identify who's entering just by measuring their height and weight. And you could turn on the appliances and keep their space ready when they entered the lab. All these things were developed in IIT Bombay in the Smart Energy Informatics Lab using this principle: sense, S for sense, M for meaningfully, A for analyze, R for remember and respond, and T for timely, which is smart, right? And so these are the useful CS concepts that were used. Lot of papers, lot of PhDs, master's theses, and many artifacts came out of the research that went on. And for the almost 10 years at IIT Bombay, and these are all the SEIL members. There is a very short video, with your permission, sir, if it can be played, we would like to play that.
Yeah, please.
Thank you.
Welcome to the Smart Energy Informatics Lab, or SEIL. We at SEIL are looking for novel approaches to reduce power consumption by employing techniques to avoid unnecessary consumption use energy resourcefully so as to flatten peaks in consumption and use less from conventional sources and more from renewable sources and storing excess energy. In doing so, we employ the SMART principle of sensing meaningfully and then analyzing, remembering, and responding in a timely manner. We have applied the SMART framework across various spaces in our academic building, such as labs, classrooms, and auditoriums.
Large meeting spaces like auditoria have built HVAC systems for conditioning and ventilation and are operated at a fixed temperature range. However, occupancy in such spaces is non-uniform, resulting in cold and hot regions within the space. We observed that with a comfort-conscious seating arrangement, the average energy consumption is 35% lower than a front-to-back seating arrangement, a considerable reduction.
The smart classroom complex in our department building consists of a combination of both large and small-sized rooms. It is designed with the dual goal of 1. Zero consumption during zero occupancy, and 2. Minimal power consumption in an occupied room. The smart classroom features a smart sensor suite to measure different parameters like temperature, humidity, radiations, etc. Fans, ACs and other appliances are actuated based on the analysis of the sensed data. We use a combination of low power, low cost, off-the-shelf hardware components with over-the-air updates and a small footprint so that our solutions can be retrofitted in new as well as existing buildings. When a person enters the smart classroom, a PIR sensor near the door is triggered and the lights turn on. Thereafter, image processing techniques like motion and skin detection help discern any change in occupancy. A few seconds later, fans and ACs turn on based on occupancy, temperature and humidity. When camera detects no humans in the space for 2 minutes, it turns off appliances in unoccupied zones, thereby reducing power consumption. Thus, in conjunction with climate-conscious room scheduling policies that factor in pre-cooling and room size, we obtain attractive energy savings of up to 58% with a payback period of 6 academic months.
In our endeavor to extend the use of unconventional energy sources, we have been exploring the use of building facades for harnessing solar energy. We are addressing the challenges posed by the shapes of modern buildings, curtailed radiations and shadowing effects to optimally determine solar potential, relevant policies and deployment strategies.
This is our crowd.
We should thank Professor Ramamritham as well as ma'am, who actually presented the work and a fantastic video. Thank you so much, sir.
Thank you.
A fantastic work that you are doing. And I guess it's a very important concept of energy, reduction in our daily use. I think it's a fantastic thing that you do. I think we have to break for lunch, and I think probably we don't want to disturb him with questions. That's my personal view, but if you want to...
We can take.
You are happy to take
Yeah, I'll be happy.
Yes.
we can let others go and we can talk to some group of people.
Yeah. So any questions, 1 or 2 questions, please, if you have any.
We are talking about smart things. I heard that smartphones, the greenhouse emission is comparable to the greenhouse emission coming from aircraft industry. So this is a thing that I heard recently. I was shocked to hear that.
Yeah.
So I think we'll be smarter if we use smartphone less.
Yeah, we don't use smartphones other than for getting picture of the terminal space. But one should remember that the smartphone does do a lot more of the activities that go on 10 phones. So we are getting a lot more for the $1 that we pay for it compared to anything else that we have seen in the past.
My request to the audience is to use smartphone less.
Yeah.
And we thank once again
Thank you very much.
Professor Ramamritham and ma'am, who assisted the final slides. Thank you, ma'am, once again for your presence, and thank you.
She's a part of the lab, so I'm thankful.